presenting work connected with the connected to the 31 tone instruments I've been building over the last years. And interestingly, this also connects very much to what Klaus Lang was introducing beforehand, this universe of mean tone temperaments. So what you can see here is the electric claviton. It's a split sharps instrument with 31 keys per octave and harmonic instrument. This is a view to my workshop in Vienna, where I started building these instruments over 10 years ago, and in the meantime I have about seven different instruments, digital and electric and electroacoustic. And at the beginning I want to give a little introduction and maybe a little different view on how I want to describe the theory behind it. For me, personally, the reasons why to go into this area was I had some clavichords and electric clavichords at my workshop, and strings broke and I wasn't sure how to repair. And then I deconstructed the instruments and attached new strings and then started to tune by myself. And all the theory before I was exposed to, and I had the honor and the opportunity to get at universities and with friends, made sense in the moment when I started to tune the instrument by myself. And the connection of proportion theory to the experience of sound. And what we can see here is the natural keys, and this looks very normal actually, but for me already contains all the necessities to expand the tonal range, because it's this dualism of functional view and intonation I want to go in detail now. So I was very happy to be in Vienna with Walter Haber, expert on hexachord theory, and it's about being aware that any note of your functional system can have a neighbor, since you name this note as any part of this ut, re, mi, fa, sol, la series. And the speciality of hexachords is that you just have one semitone. And this one semitone also we just saw in this visualization in the presentation beforehand, is always mi, fa, or fa, mi. And this comes, as I will show later, from the retransposed fifths. Old story, I guess you're familiar with that, but the speciality I want to point out is that if you name the note by any syllable of any solmization syllable, then you're able to define the neighborhood of the note. And that's the reason why the black keys are introduced. And that's the reason why many black keys are introduced. And the temperament of this functional system is the reason why split sharps are introduced. Yeah, we see that those hexachords, actually we see 3 different hexachords that are interlocked. And the mutation formula is ut to fa. So we see ut starting from G to F, fa, and then ut is modulating to, fa is modulating to ut, going to F, fa, again modulated to ut. So before that, and before polyphony was introduced, of course you know that, but I want to connect this with solmization and with the Utquian Laxis phrase. We see that three different tetrachord species are interlocked, so 3 common modes. And this leads to this can be expanded to 5 limit, as we have seen beforehand, just to go through this a little quicker. And if it's expanded to 3 limits, so the major third is 5 to 4, then you have these comma problems. And historically, there were instruments built for having also divided wide keys and lower keys in order to be able to distinguish the commas. As we can see here, that's a 5 limit lattice. You have 3 to 2 and 5 to 4, and in fact this creates 2 Ds, 2 As, and 2 F sharps and 2 B flats and so on. This is a prototype. Maybe in the future I will go into that direction again. But we can see here, if 5 limit would be applied to that concept of dividing the keys in order to be able to make more, to have a wider tonal range, then you also need to divide the D and the A, because one time it's part of the 0 and then it's part of the -1 axis. But the last 10 years I didn't go into this direction. I was much more fascinated about mean tone, temperament, where you leave out all those questions of the comma, which means only dealing with the diesis, and the diesis is the difference of the major thirds. Of 5 to 4. What we see here is just a short summary of the core of this tuning that can be open chain, that is quarter comma mean tone, but it can also be closed, as I use it on this special instrument, the Claviton, that is 31 pitches per octave. The speciality is 5 to 4 is almost pure, and all those other 3 limit intervals are slightly or heavenly tempered. So 9 to 8 is, as we see, half a comma flat, and the 4th and the 5th are deviating quarter comma, which results beating intervals, as we heard before. Okay, this leads to the black keys of the first row in order to be able to make cadences of the widened hexachordal, interlocked hexachordal series. So that's also the reason why we have in the first row starting from C, then C sharp, D, E flat, and so on. So it's a mirrored system, it's not an isomorphic layout. What I'm showing here is again interlocked hexachords. So the low visualization shows the F hexachord and the B flat hexachord, and as soon as you continue the formula which I was introducing beforehand, ut to far or far to ut, then you need to introduce more split, more flat and sharp accidentials. So as far as we can see now, there is no conflict so far for the black keys, because between all the white keys now there is a key introduced. But if you want to go further, we need to introduce a second row. And we see here 2 hexachords. That's the F sharp hexachord and the B hexachord. Actually, it's the B hexachord followed by the F sharp hexachord, because in the logic I was saying beforehand, it's the ut-fa mutation. So you have the B hexachord, and then it's a servum chord, hexachord, which is below that one. And so on, to both directions. So the chain gets longer and longer to both directions, as we can see here. The yellow one is the sharps, and you can read it from right to left. You have way up there, that's the C sharp hexachord, A sharp, G sharp, F sharp, E sharp, D sharp, C sharp. Then followed by the G sharp hexachord, E sharp, D sharp, C sharp, E sharp, A sharp, G sharp. Then the D sharp hexachord, C. So here, that's the D sharp hexachord. From top to bottom, it's B sharp, A sharp, G sharp, F double sharp. So that's the first moment where the third row is necessary, and that's also the moment where it's beyond 19. So before we get the chance to get the introduction to 19, and for this special temperament of quarter comma, the F sharp is not the same like the G flat. F double sharp is not the same like the G flat. And if you want to read the top, then it's from left to right. So it's ut, re, mi, fa, sol, la, starting from the G flat. Here. G flat, A flat, B flat, C flat. So again, that's the moment where it's beyond the 19. C flat for the first time for the flats, and F double sharp for the first time for the sharps. So the ascending hexachords for the flat direction are G, then C flat, then F flat, then B double flat, followed by E double flat. So we are here. G flat, C flat, F flat, B double flat. That's the first time when no, there's no first time. E double flat, this is the first time, A double flat. So the fourth row is introduced, and the fourth row for the sharps at first occurs for the D double sharp, which is here. And of course the D double sharp is necessary if you want to make a cadence in E sharp. So here is the E sharp hexachord. And if you want to make a cadence, of course you need the D double sharp. That was a cadence in E sharp, which from its sound quality sounds totally the same like everywhere else, because it's an equal tempo system. Okay, that's the odd region. Since I was mentioning 31 is circular, there needs to be a position of enharmonic change. And the enharmonic change is done at the double sharps and double flats. So we see this one, which is, I call it A double sharp. And this A double sharp is the same like C double flat. And the hexachord from left to right, here, that's the G double flat hexachord with enharmonic change names inside. G double flat, A double flat, B double flat, then C double flat, which is A double sharp, D double flat, and E double flat. the ascending hexachords sound like, that's G double flat, then C double flat, C double sharp, C double flat, which is A double sharp, and then D double sharp, G double sharp, C double sharp, and then after F double sharp, it continuously walks back to the C, as we know from this, because the F double sharp is here, and then I will demonstrate going through 31 tones, 31 hexachords. Okay, 31 tone is a fifth of a tone tonal space. All those notes I was playing now appear between the whole step as a 5th division of the tone. So the arcs show the chromatic steps from the C to C sharp and C double sharp, and again from D to D flat and D double flat. And since it's 5, there is no equal division of the tone, which sounds like this. True diesis and enharmonically changed diesis. So the very first one is the true diesis because it's a double diminished second. And then we have an enharmonically changed diesis from D double flat to C sharp, which actually is E triple flat, but that doesn't matter so much. And then we have D flat to C sharp to D flat, which is a true diesis of 128 to 125 approximation in quarter common midtone, but in this case it's a little flatter. And then we have D flat to C double sharp, which is again the enharmonically changed diesis, and then true diesis from C sharp, C double sharp to D. So, the smallest intervals of this tuning, as I was saying, it's basically morphed 5 limit, and with all the other intervals, it's actually a very nice 7 limit approximation, and even further, I will explain that afterwards and show some techniques how to work on this. We see here step 1, that's the diesis of A double flat to G, which is about 128 to 125. Then the chromatic stuff is actually very close to 23 to 22. So the usual limit conception in this case is not that helpful. I will go into this a little bit later. Then we have 15 to 14, which just deviates 2 cents to the mi fa diatonic step, and then we have the neutral step of 12 to 11, which is very precise, and 19 to 17 again for the whole step, which is a little bizarre since we derived it from 3, so it's 9 to 8 minus a half of a comma is very close to 19 to 17, which is fun. Okay, this example what I was playing before when I showed the the transposing of the major thirds. This is written as if it was just intonation. And as I will explain later, there is the possibility to use 31 as if it was just intonation for composition concepts and so on, and also for improvising. Although in reality it deviates a little. As far as quarter common mean tone, that's the tuning before the logarithms were introduced and everybody was informed that a circular system is possible with equal temperament. The quarter common mean tone tuning, in fact, includes this the stacking of 5 to 4 in just intonation. 5 to 4, 25 to 16, 125 to 64, and the diesis. And since now I have 31 pitches, I can decide where to put the diesis. And then do some pitch shifting as I was doing before. That's what I was just playing. You see, as 31 is a prime number, you can go through all tones with every interval. I go through all 31 positions using the major third. Okay, little composition of mine connected to what I was saying so far. This is a little study of tetrachords making small cadences, and as we can see here, it's actually in E major. Yeah. But involves much more pitches actually than an E major scale would normally be in terms of octave scales. So the hexachordal concept is not an octave repeating thing. It's more to say what notes are necessary to make cadences at. And they are, of course, the notes of the hexachords themselves. And if you want to make cadences on these notes of the hexachords, of course you need the subsemitonium of every and those notes appear in this composition. D sharp, of course, to have the cadence in E. Then going to A, you need, of course, the G sharp to reach the A. Then you need the E sharp and the F sharp to go to to F sharp minor, and then you need a B sharp in order to make the cadence of C sharp minor here, and so on. And you need, of course, the A sharp to make a cadence in B, which appears chromatically shifted as a B sharp here. And the so-called fourth minor, which is actually hexachordal change. You have the C natural here for the cadence at the end. What happens? So, this is an interval that's beyond the scenario. We just were introduced of this category of pseudo 5 limit intervals, and now we have within this system some intervals that can occur. Still we are navigating diatonically, as I would call this, because we just use the possibility of interlocking tetrachords and hexachords, but we have a sound like this. And this sound, of course, is not part of the 5 limit or scenario. Very similar to the augmented 6th chord. So, at special situations, like augmented or chromatically changed 6 chords, or the diminished chord, which in fact this is a diminished chord, D sharp, F sharp, that's the very last, D sharp, F sharp, A and C, and the D sharp to the C is a septimal interval, which is a very close approximation to 12 to 7. So the spectral neighbors of this one could be, but in this case it appears as both of the notes are part of different hexachords. So the C, although we just found out that there's a spectral interpretation of this one, but in this case diatonically it's a Fa. Re, mi, Fa, and of course the D sharp must be a Mi. Mi, Fa, Sol, La, and then Mi, Fa, Fa turns into Re, Re, Mi, Fa. And that fascinates me very much, that you have both the possibility of both views at the same time. You can call it, you can name the interval by a spectral definition, but at the same time also with the concept of the expanded hexachordal concept. So for improvising, all those techniques can be applied. And I was trying to transfer the fingerings of the piano to the claviton, which was easy for some regions, but when reaching, for instance, E major, for a cadence in E major, then already I need to work on new fingerings. Because the chromatic scale, as I will show afterwards, and the circulating motifs around the tones involve different tones and different fingerings. But the way you would notate this cadence is exactly the way how I visualize it on the piano. And this is a little different to, let's say, intonation visualization of this tuning, because if you're a string instrument or a guitar player, you go by the ascending pitches. In this case, I don't go at first by the, after the ascending pitches, because as we were seeing before, I was deriving this from the hexachords and for the interlocked tetrachords. And the microtonality is just the result of this process, but it's not the initial idea. So all the fingerings for all those scales are not the first intuitive thing you would do on this keyboard, which is different to, let's say, a glissando on a violin or a glissando on a 31-tone guitar or whatever. So this seems like a big disadvantage, but actually it's the biggest advantage of this keyboard because it can be played without looking at it. If you have an isomorphic keyboard, which means you have the same fingering for any chord and you just go here and you have everywhere a major chord, then you don't know where you are actually. So with this, if I play F minor instead of E sharp minor, it's a completely different haptic experience and a completely different diatonic region I need to master beforehand in terms of knowing the hexachord positions. And I worked on some techniques to improve that, like canon of tetrachords or some scale exercise. Scale exercise means hexachord scale exercise, and yeah, there's slow progress. This is what I was showing before. If you do enharmonic change in 31, then you reach the higher prime regions. Beforehand, it's diatonic, and it's kind of pseudo 5 limit. As we know, have seen beforehand, actually this, if we go in detail of the sound, it's not 5 limit. It's 34 to 19, which is prime limit of 19, but leaves out everything below. So again, the concept of this limit is not that useful in this case. It just, I will give a proposal for a different method of naming this later. But as far as we can see, if you change the enharmonic of this of these well-known intervals, we are able to play 7 limit intervals. To take this chord diatonically, because we know the augmented sixth is, in terms of hexachordal theory, it's fa and mi. Fa and mi, which leads to. But if we go one step back, we also can use these new chords for intonating the functional structure. So for instance, this B flat 7th chord, also we can use those possibilities of the intonation side of this 31 tone temperament to intonate this, let's say, dominant chord in 7 limit. There are two ways, of course. Either flattening the melody note or flattening, sharpening the bass. And this can be expanded to 9th chords, of course. Situations, I can decide if the melody, if the diatonic logic of the melody is important or of the bass. some studies to go step by step. Okay, that was the 7 limit. And in this example, I already played some pseudo 11 limit intonations. So again, what we see here may be not that obvious at first sight because we have some diatonic accidentals, but what I want to explain is a spectral thing. In fact, this G double flat can be used as if it was tuned purely to 11 to 8. Although there's a different logic behind, and the deviation is about 10 cents. But if I want to use the chords imitating the sounds of the harmonic series, I of course can involve those sounds. So for those who are interested, this one is actually very close to 175 instead of 176, which is 11. So the deviation, and this is a comma phenomenon in 31, we have 176 to 175. But depends on the situation. And works. And then, of course, 13, which is G double sharp. And G double sharp, again, is about 10 to 12 cents of 12 video off to the just intonation. And there's again some odd comma, there's a odd comma situation, 105 to 104. And if we want to think that this is not that important, we can use the G double sharp, which comes from a very different diatonic region than the A, of course. So again, we have this functional view that says G double sharp can be ut, re, mi, fa, sol, la, but at the same time it can be an intonation of something else. In this case, I use it as an intonation of the A. So and 7 are almost pure in this tuning. The 5th is tempered, as we know. And those higher primes they still work. Okay, so actually the concept of limit in this case is not that useful because, as we saw beforehand, there are some intervals that are very important and they leave out a lot of different prime numbers. And then again, you have for a very important interval such as the major second, you have 19 to 17, and there is no ascending concept behind. So I introduced this different terminology to talk about the style of the primes involved. And in this case, tempered 3, 5 and 7 as if they were just, and then pseudo 11 and 13, and this can be expanded to pseudo 23, among others. So for instance, if you have this of yesterday, the Macam thing, where he said it's basically 3 limit plus adding some 13, then this would look like 3, 13. Because there's no 5 and there's no 7, there's no 11. For instance. Or 12 EDO would look like T3 but in fact T3 and pseudo 17, pseudo 19. Okay. With this spectral technique, it's possible to analyze one and the same interval from different sides. This can be important for composing, such as comparing it to just intonation. So we have the major second, as I was saying before, 19 to 17 we see in the second visualization, but also with a different concept. Not going too much in detail. If anyone is interested, I can explain afterwards. But actually, I'm deriving this major second plus an octave via different spectral intervals of this tuning, like 5 to 4 for the second example, 5 to 4, then 12 to 11, then minor third, and then 11 harmonic, which leads to something else if all those numbers would be added in just intonation. But in this case, I can use it as if it was just intonation. Just for, for instance, the first interval, of course. Second one, 12 to 11. Different root. As soon as I say this interval now is treated as if it was just, I can take all the approximations of just intonation to this interval, and it somehow works, and you can work on integrating this to a functional sound, to any situation you are in at composing, and then you need to just say if it's just enough or not. Okay, so the Wolf. The Wolf situation actually is a just intonation situation in 31. That's very unexpected because, as we heard, the Wolf is something to be avoided. But when the concept of the prime numbers, of the limit, is expanded, and we want to also integrate the sound of 19 and 11 and 17th harmonic to our area of consonances. Consonance means, in this case, just physically that the sound works close to this ratio. So there's no deviation coming from another whole number ratio. In this case, that's the Wolf fourth compared to the tempered mean tone fourth. And what's funny, the Wolf is much more in tune than the tempered fourth. Because we hear the deviation and we hear the beating. And now I go to the Wolf. It's totally stable. That's just an interesting phenomenon because those intervals normally are tried to avoid in terms of consonant playing, but this term of consonants is just it's a matter of definition. So if we say we are very consonant in the area of 19 and 17, then we want to play this over and over. So I can't play the root here because I don't have the root of 17 to 13 in this tuning. But if you listen closer to the what's it called?
Periodicity.
Yeah.
Summation.
The summation, yeah, right. one will appear. Then 19 to 17, that's the whole step. And the inversion 26 to 19. Just okay. This is very practical for improvising, for using 31 as a tool to imitate the harmonic series as I was playing before. So this is the area of 7 to 14. And in terms of the whole steps and the neutral steps, there for every tone there is a very close approximation. And I try to transpose this to work on some fingerings, and with with the metronome have some rhythmic concepts, and then integrating this to be able to add this to some, let's say, chord progression situations like the one with F minor to B flat to E flat. Again, so the F minor is diatonic. The dominant chord is spectral. I can also add the spectral intonation for the one, then it sounds like this. And so on. I can also make a spectral intonation of the second minor chord. And so on. I was trying to find a step-by-step concept for this. So this is how it looks on the keyboard. For 7 to 14 in C. So C is the 1, A sharp, as we had seen beforehand. A sharp is the septimal 7th, pseudo 9, 10 precise, pseudo 11, tempered 5th, pseudo 13, and again 14, which is the octave of 7. Okay, different concept. At the beginning, I did not have the instruments available yet, but I had some concepts and some ideas to play this music with expanded mid-tone temperament in my ensemble Zielton, with David Tonic on guitar, 31-tone guitar, and Valentin do it on drum set. And one of the technique was to use a Rhodes piano and later on a grand piano tuned in subset tuning. So we see how those pitches are different in every octave. And this comes from the pieces I was practicing at that time in order to have the most technically demanding passages available. And for all other situations, I changed some fingerings or octaves for the compositions of David at that time. And later on, I was becoming very used to this temperament, not the temperament, to the subset idea, and also made the improvised record, a piano tuned to this subset tuning. And we see how those notes are different every octave and how this would be, how the fingerings would look like on the claviton. So for instance, if I start here at the F is normal, then the G flat is the second row, A flat second row, B flat, and then I have, instead of the A double sharp, as we know the A double sharp is one diesis below the B, I have this one. This is my pseudo B, that's the A double sharp, and so on. And then I have a very unusual scale. And so on. And for instance, this composition. Totally exploring in this field of enharmonically changing octaves. And in this case, I was very aware of the precise tuning. But later on, I used this technique, tuning the piano, and then forget what the precise tuning was, in order to explore very intuitively. Okay, the ensemble I was mentioning, that's C-tone. We're playing in 31 with all the instruments we have built so far. So on the left side you see the Claviton keyboard. This one is here. That's the large one. Then there's a bass controller as well, and the keyboard for the electric clavichord. And we have an 8-string acoustic guitar, 8-string tenor guitar, and 6-string 31-tone guitar and a 31-tone bass. Another subset was actually at the very beginning of the process of this band, because I was doing arrangements of field recordings. So the music I was listening at that time was a balafon recordings of Western Africa called Gil tradition. And I was doing transcription of those pieces I found that were musically very interesting, because they not only involved some thriving rhythms, but also arrangements with some tempo modulations. And out of that Ziel transcription, the name of the band Zilton was created, and all the pieces afterwards written for this band were based on the same basic techniques, as they have to involve 7th limit just intonation or 31 EDO, and rhythmic modulation concept based on, again, whole numbers. I will explain this a little later. We can see here that's again a subset for 31, and all those intervals inside, they're about to be pure in 31 tone equal temperament. First I was tuning this by ear, that's why this little treatise that's available on my website is called Tuning the Notes of the Piece Tone by Ear. I was sitting down at the clavichord I was mentioning before, and I deconstructed. This was in the time before I had built these instruments. And I was tuning this tuning by ear, actually starting from the middle C, and then have a septimal 7th above, and the C to be a septimal 7th of a D, of a E double flat. And so I had the chance to get very close to the intonation of this balafon, but I could work with the visualization of mid-tone temperament. And I really enjoyed this moment to bring those two worlds together. Okay, that's the piece. What you can see here, enharmonic notation, and the time signatures are in, they also have a whole ratios behind. So this was the transcription technique actually to get very close to the tempo modulations of the recording. And of course we don't know if this was the technique of the musicians when they played it. Okay, I play this, please. This I was mentioning beforehand. This is again a subset tuning that was derived from the previous one, but when I tuned this one, I had no idea afterwards how the notes are. So I was going very fresh to the piano and explored what I found, and some compositions came out of that process. I have, since that time, there are two hammer-clavier instruments at my workshop, and I tuned those hammer-clavier instruments to the subsets, and then I was composing on this. And this is a piece that came out of that process. I'm very sure I would not have composed this without the subset technique. I can play it right now. Take a different sound. So this piece just has 12 pitches per octave. of course, because it's composed on the piano. A third technique. You can analyze the intervals of this equal tempered system by the vectors, if you're familiar with the terminology of set theory, by the vectors of the intervals. Like, as I was saying before, there's a division by 5 of the tone. That means the major third is 10, and the mi-fa semitone is 3. So for the fourth, we have 13, because 0, 5, 10, that's the major third, and then we have plus 3, that's the fourth. Actually, 0, 5, 10, 13 sounds like this, of course. And then 18 is plus 5 again, that's 13, plus 5 is 18, 23, and again 0. If you have these numbers, there are very different possibilities popping up actually. So, before I was saying, there is no possibility to divide the tone equally, as we are used to do in 12 equal temperament, for instance. Because the tone is divided by 5. But if there is one octave between, then the situation occurs to be very different actually, because 5 plus 31 is 36, and 36 of course is dividable equally. For instance, by 18, this one we already know, because that's just stacking fifth, but it's also divisible by 3, so that means 12 plus 12 plus 12. And 12 is, as we can compare, 13 is the fourth, so 12 is one step below the fourth. Again, another one. And we have this sound. And with this technique, you can divide any interval by any number. That's very interesting for composing. The vectors compared. Here we have an interlocked hexachord, a hexachord constructed by interlocking tetrachords in a different way than we have seen before, because it's not 3 common notes, it's just 2 common notes. This situation is very often used. It's just a cadence in minor with a major dominant in the modern terminology. It's not about being modern, but mostly it's called modern. Actually, okay, we can go into this afterwards. And then the chord out of this named by the vectors of 12 EDO compared to the vectors of 31. And then we can see second is 5 and 5, which means the fourth is 13, and 6, which means the tritone is 16. So with these numbers, there are at least 3 different categories of how they are used in this context. They can be the name of the intervals, confusingly with the names of the harmonic series, and the names of the interval vectors of the EDO, and the names of the harmonic series. So this is how the chromatic scale looks at the claviton. The chromatic scale means the series of 2. Chromatic scale at the piano actually is an enharmonically changed chromatic scale. But in this case, it's also an enharmonically changed chromatic scale, but at a different point. You start at C, then have a C sharp, a C double sharp. That's plus 2, plus 2. And then you change enharmonically, because the C triple sharp is the same as E double flat. So C, C sharp, C double sharp, E double flat, E flat, and E. Sounds like this. numbers, the chromatic scale cannot be octave repeating because 31 is not dividable by 2. So there are 2 octaves necessary in order to close the whole scale. And so on. That's the Mi-Fa scale, actually having a lower and the upper diatonic semitone of every tone of the EDO notes. In this case, it's the series of 3. So 3 plus 3 is 6, plus 3 is 9, 12, 15, 18. And 18 we know so far is the 5th, and that's what we can see here, G to D, and you have 6 steps inside. This one works very well for instance, for the neutral area between 10 and 14 spectrally set. For instance, when improvising before, I was using those fingerings of the chromatic scale for 10, 11, 12, and 13, and the diatonic Mi-Fa scale can be used for the septimal whole step. Very quickly. For instance, or for the whole step, then the that's a piece I want to play. That involves most of the techniques I've been talking about so far. different example with some spectral chords coming out of the subset. Time is left. Yeah, so maybe I can show some instruments that are built at my workshop, but not for myself. I'm very happy to share the passion about this spiritual instrument thing. I'm not able yet to make a huge number of instruments in my workshop, but still there's some people interested to come and work with me on the instruments several weeks or months. And this is the instrument of Amir Ahmadi, a good friend and composer living in Vienna. And this is the instrument of Valentin Duet, the drummer I'm playing with, a Zilton. Then this is another instrument I built for Tanaka 5-limit instrument, for 5-limit harmonium. And here you can see some of the instruments at the workshop. Yeah, I guess so far. Thank you.